Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology. So I also took my Bachelor's of Science at this institution as well in the Pharmaceutical Chemistry program. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or with tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today's session. Okay, so question number 1 asks, when dissolved in water, which compound is generally considered to be an Arrhenius acid? NH3, KCN, NaOH, H2CO3. So first I'm just going to write down the definition of Arrhenius acids. So basically these are compounds that dissociate in water to form H+, or protons. Okay, so now let's look at all of our different options. They give us NH3, KCN, NaOH, and also H2CO3. So now I'm just going to write out what ions they form in water. So for the first one, when NH3 reacts with water, it actually gets protonated to become NH4 plus an OH minus ion. So this isn't an Arrhenius acid. Let's look at the next one, KCN, potassium cyanide in water. Gives us like potassium hydroxide. Plus hydrogen cyanide. So this also doesn't really form the protons since HCN is formed. When we have sodium hydroxide, you actually just get NaOH aqueous, like if this was a solid, plus water as well. So it's not sodium hydroxide either. Plus everyone knows that that is like a very popular base. So now let's look at our last answer. So this actually gives us the H3O plus ion, which is essentially just protonated water. I'll put that in brackets. So this is our answer for the Arrhenius acid, since when it dissociates in water, it forms the protons. Let's check out the answer from our junior tutor. Okay, so they said the same thing. Arrhenius acid is H plus stonar. I'm guessing in water. Arrhenius base is when you have an OH minus formed when dissociated in water. And then they kind of broke it up for us. ACN is a salt. Yep, so this answer is correct. Okay, so let's move on to question number 2. Identify the gas particle that travels the slowest. So before I go over all the different options, I'm just going to write down this formula of kinetic energy. Basically, it is as follows, where it is equal to the mass, half of the mass times like the velocity squared. So if I were to try to isolate mass and rearrange the equation a bit, you get the following. And already you'll notice that the mass is inversely proportional to velocity. So I'm going to write that down. So basically, the larger molecule you have, the slower it'll move. So that kind of makes sense. But basically, this is the expression that can kind of prove that. So now let's look at our different options. They give us carbon monoxide, hydrogen, nitrogen, neon, and oxygen. So now I'm just going to write down their molar masses, their respective molar masses. This is just like an estimate, no decimals involved. Okay, so after I wrote down all of their different molar masses, I'm now just going to see which one is the heaviest. And in this case, it is the oxygen with a molar mass of 32. So that will be the gas particle that travels the slowest. Okay. Okay. So I don't know where they got this gas mass from. So it looks like it's the solution to like a different question altogether. So I'm just going to write down what I did. Okay, so I said since mass is inversely proportional to velocity/speed, then the heaviest molecule will travel the slowest. By comparing the molar masses of all the gas particles, O2 is the heaviest, therefore it will move the slowest. Now let's move on to question number 3. Tartaric acid is the white powdery substance that coats sour candies such as Sour Patch Kids. Oh, that's cool. The combustion analysis of a 12.01 gram sample of tartaric acid, which contains only carbon, hydrogen, and oxygen, produced 14.08 grams of CO2 and 4.32 grams of H2O. Find the empirical formula for tartaric acid. Okay, so this is one of those multi-step questions. So first I'm just going to write down the mass of tartaric acid that we started with. This is given in the question. It was only like 12.01 grams. And first I'm going to calculate how many grams of carbon was released after the combustion analysis. So basically, to find the mass of the carbon, let me write it as step 1. We know that the mass of CO2 is 14.08 grams. I'm going to write out clear units so that you can see where everything came from and also how it cancels out in the end. First thing I'm going to do is find the moles of CO2 that was released. So to do that, it's just mass over molar mass. So the mass was 14. The molar mass of CO2 is 44 grams per mole. Then I'll also just put CO2 there. So we then get a number of moles of 0.32 moles of CO2. But now I'm interested in finding out how many moles of carbon is in that many moles of the CO2. So if you look at the formula for CO2, you'll see that only 1 mole of carbon is in 1 mole of CO2. So you'll see that these units will cancel out. And then to find the grams, basically I'm also going to multiply my moles by the molar mass of carbon, which is 12 grams per mole. And this is the molar mass of carbon. So if we were to do all of the math, you'll see the moles of carbon cancel out as well. And then we're left with a value of 3.84 grams of carbon. So now let's do the same thing for hydrogen. So 4.32 grams of water was produced after the combustion. And the molar mass of water is 18 grams per mole. So now I'm going to find the number of moles of water just by dividing those two values. And you get 0.24 moles of H2O. And then to find out the moles of hydrogen, there are 2 moles of hydrogen for every 1 mole of water. because it's H2O. And then also multiplying by the molar mass of hydrogen, which is basically 1 gram per mole. We end up with 0.4848 grams of hydrogen. So now, just by doing the law of conservation of mass, if I know that we had a total of 12.01 grams of tartaric acid, I'm going to subtract the 3.84 grams of carbon that was there, and going to subtract the 0.4848 grams of hydrogen that was there. And then we find out that 7.69 grams of oxygen makes up that tartaric acid. So for step 4, I'm now going to find the moles of the atoms. It's kind of like one of those multi-step, like redundant questions. But basically, I'll just do the 3.84 grams of carbon divided by its molar mass, which is 12 grams per mole. So we have 0.32 moles of carbon. Then let's do the same thing for hydrogen. 0.4848 grams of hydrogen divided by its molar mass, which is 1.01 grams per mole. And we get 0.48 moles of hydrogen. And then we do the same thing for oxygen. 7.69 grams divided by the molar mass of oxygen is 16 grams per mole. And we get 0.48 moles of oxygen. Okay, so for this last step, I'm going to try to write out this empirical formula just by using the mole values that we got. So for carbon, it was 0.32. For hydrogen, it was 0.48. And then for oxygen, it was also 0.48. So I want to try to get these values not in the decimal form. So the first step I'm going to do is to divide everything by the lowest value, which is 0.32. And then we get C1, H 1.5, and also O 1.5. But again, I don't want these in decimals, so I'm now just going to multiply it out by 2, just so that we can get whole numbers. So it's now C2, H3, O3 is empirical formula. Okay, so let's check out the answer from our junior tutor. They got all the grams of carbon, hydrogen, and oxygen. They got the moles, 0.32, 0.48, 0.48. They divided each by 0.32. and then multiplied by 2 to get C2H3O3. So this solution is correct. Okay, so now let's move on to question number 4. Add one or more curved arrows to show the movement of electrons in the following reaction. So basically we start off with a chlorine molecule, Cl2. And I'm also going to draw in the electrons, just so we can check out the movement of electrons in the question. So basically it looks like the bond breaks. Which is unlikely in situations like this since Cl2 is very strong. But for the sake of the question, let's just say that the bond is broken and we're left with 2 chlorine atoms with like a free radical for each. Basically, to show this mechanism and to show the breaking of the bond, I'm going to draw these half arrows. Sorry, that looks bad. A half arrow going on that chlorine and a half arrow going on that side. So basically, half arrows show the movement of only one electron. So usually when we have a full arrow, that's like the movement of 2 electrons. But to show the movement of the one, we're going to use these half arrows. And this is for the homolysis. So that basically means like the breaking of the bond. Of a bond. And basically this gives free radicals. So when you have atoms that look like this, that was like produced and it has a single electron that isn't paired with another electron, then this is an example of a free radical. So usually they're very like unstable and wouldn't last that long in a reaction. Okay, so the junior tutor said the same thing. They showed the half arrows. This bond undergoes homolytic fission to give only free radicals. This solution is correct. Okay, so let's move on to question number 5. Draw the organic product in each of the following reactions. Include formal charges if applicable. Omit any inorganic byproducts or ions. Okay, so let's draw out the mechanism for this reaction. We have like a cyclohexane ring with a bromine. And first it reacts with sodium cyanide. So I'm going to draw out a negatively charged cyanide ion, just coming in to replace the bromine. So basically when you have organic reactions, almost all the time bromine acts as a leaving group. And then you're left with the following structure. Okay, so after it reacts with the sodium cyanide, then the lithium aluminum hydride comes in, and basically this is a very good reducing agent. Let me draw it in blue. Okay, so this is basically what the reagent looks like if you were to look at the charges. So the aluminum attacks at the carbon. And goes there. But basically this is like a multi-step mechanism that occurs. And eventually the aluminum is bonded with the nitrogen. And then you get this intermediate. So now this negative charge will come and reduce that double bond again. So that's basically the role of lithium aluminum hydride, is that it reduces your triple and your double bonds to make just single bonds. So now the role of the H3O plus and the OH minus is that they come in and get rid of the aluminum hydride. And our final product is just this new amine group and carbon that replaced the bromine in the end. Let's see the answer from our junior tutor. They have the cyanide replace the bromine, and then after it is reacted with the lithium aluminum hydride, that triple bond gets reduced twice, and then we're left with just a single bonded carbon with an amine group. The solution is correct. Okay, so now let's move on to question number 6. pKa values of phosphoric acid are 2.2, 7.2, and 12.7. A phosphate buffer of pH equals 7.4 can be prepared using different options. But they give us the correct answer. They just want to know, how did we get that answer? Okay, so this is question 6, I believe. So basically the definition of a buffer is that it has both acidic, and basic properties. So they give us the pKa values for phosphoric acid. So let me write out phosphoric acid. And I'll show how it first dissociates into a proton plus H2PO4 minus. So the pKa for this reaction is equal to 2.2. And you'll notice that this means that it's very acidic. So that means it's very likely for the phosphoric acid to donate one of its protons. So this is a polyprotic compound, so it's actually going to undergo deprotonation again. So H2PO4 minus dissociates to another proton plus HPO4 2 minus, and they said that this pKa is equal to 7.2. This is more of like a neutral pKa value, but it's still like a little less than the phosphate buffer that we're looking for. So let's also look at what happens if HPO4 2 minus loses one of its protons. Yet again, you end up with PO4 3 minus, and the pKa of this is 12.7. So this just means that HPO4 2 minus is considered like a weak acid. It's not likely for it to donate one of its protons. So to answer the question, when you want to create a buffer that has a pH of 7.4, we're going to need both H2PO4 minus and HPO4 2 minus, just to make a little more basic. Because if we use just straight up phosphoric acid, whose pKa is 2.2, that'll affect the pH of the buffer so much that your buffer won't even be like a neutral pH, it'll just be so much more lower. So that's why we need the H2PO4 and HPO4 2 minus. So let's see the answer from our junior tutor. The main concept here is buffers, both acidic and basic properties. They give us 3 pKa values. These are known as the equivalence points, or pH at which the acid and base are equal, hence making a great buffer. So you can see there are 3 hydrogens, making it extremely acidic, therefore it is the one that has the lowest pKa. And then they have the reaction that gives a pKa of 7.2. And then the last step is the hardest to remove, the hydrogen. It has a pKa of 12.7. If you want a phosphate buffer at 7.4, you can't only use H2PO4, which has a pKa of 7.2. So to compensate, you need some of the HPO4 minus 2 degradation with a pKa of 12.7 to balance it out. This solution is correct. Okay, so let's move on to question number 7. How many inner, outer, and valence electrons are present in an atom of each of the following elements? So first, let's look at bromine. Its atomic number, which I'll just use as Z from now on, is equal to 35. And it's also in group 7A. So this is one of the main groups on the periodic table. And the 7 actually indicates how many valence electrons are present in an atom of bromine. So since there are 7 valence electrons in bromine, and there are 35 electrons in total, therefore there are 28 inner electrons. So let's try out this same kind of concept with the cesium. Its atomic number is 55. On the periodic table, it's in group 1A. So therefore there's 1 valence electrons. So therefore there are 54 inner electrons. For C, we have chromium. So this is more of like it's not as simple as the other elements since it is a transition metal. So we can't just like predict its valence electrons in the same way, but we can look at its electron configuration, which is argon 3d5 4s1. So if we look at its electron configuration, you'll see that there are 6 valence electrons. And then if we did 24 minus 6, you get 18 inner electrons. Okay, let's do the same thing for strontium. Its atomic number is 38. It's in group 2A. So 38 minus 2 is equal to 36. And then our last option, which is fluorine. Its atomic number is just 9. It's in group 7A. So it has 7 valence electrons. But this time it only has 2 inner electrons. Let's look at the answer from our junior tutor. First, we must write the electron configuration of bromine. Yeah, sure. And they got 7 valence electrons. And they did atomic number minus valence and got 28. Outer electrons are those in the highest energy level. They spend most of their time farthest from the nucleus. Bromine is in group number 7. Similar basis, this is the electron configuration of cesium. 54 inner electrons and 1 valence. Chromium has 23. Oh. Maybe they just did the math wrong. I'll just fix that later. The strontium has that electron configuration. 36 inner electrons, 2 valence. For fluorine, fluorine has 2 inner electrons and 7 outer electrons. I'm just going to correct. Everything else was correct, so I'm just going to do this little note. Chromium should have 6 valence electrons and 18 inner electrons. Yeah, let me look up the atomic number of chromium just to double check. Okay, so yeah, so there's 24. And that is its electron configuration. I'm still going to say the solution was correct. And I think we have time for one more question. In each reaction box, place the best reagent or reactant from the list below. So first we have an alcohol group that reacts. It looks like they added a new carbon oxygen bond plus an aldehyde. I'm just going to add the reagents real quick. So if we start off with an alcohol group, in order to add our carbon group, which should contain an extra 2 carbons and an oxygen, we're looking at ethylene oxide. I need to deprotonate my alcohol. So the best reagent for that is this sodium hydride. Basically, it's a really strong base that is able to deprotonate that alcohol to get O-. So next, I'm going to react it with the ethylene oxide. So this is the group that we want to add on to the other side of our oxygen. And basically it looks like this epoxy. And the product of this reaction is as follows. The epoxide ring kind of opens up like that, and you're left with the added group. So they kind of already told us that there is a neutralization reaction that occurs like in between. And what this step does is that it adds proton to that negatively charged oxygen. And then basically to convert from an alcohol to an aldehyde, out of all the different reagents on the list, the best one to do that is PCC. Okay, so we end up with our final product is 2-benzyl oxyacetaldehyde. Okay, so just some quick organic chemistry involved. So let's see the answer from our junior tutor. Use the sodium hydride, ethylene oxide, and then the neutralization gives us the added carbon group with the OH, PCC, then oxidizes our alcohol to make an aldehyde. This solution is correct. Okay, so that is all the time that we have for today. If you like today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. Also, if you liked today's video, go ahead and give it a thumbs up and comment. And don't forget to share it with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.